Hey everybody, in this video we are going to go over a rate question that requires calculus and knowledge about equilibrium from Unit 10. So this question will be very challenging because it involves calculus first of all, and it is from the Chemistry Olympiad, which means that it is going to be interesting to do. So this question states that a reaction that is in equilibrium is reversible with KEQ equal to 1.00. The forward reaction is first order in A, and a reaction initially containing only A at an initial concentration of A0, which plot will be linear over the course of the reaction. So basically, what we have to do is that we have to find a way to make the rate a line. So if you remember from video 9.2, we made lines from the integrated rate laws. So from here, we actually have to create an integrated rate law from the information we are given. And notice how before we would have just one reactant A turning into B, but now we actually have B turning back into A, so we have to consider the rate of that as well in our calculations. So to start off, let's calculate the equilibrium concentrations of A and B, because it says initially the initial concentration is A0, but remember this is not an equilibrium since you have no products, and for it to reach equilibrium there has to be a certain amount of products over reactants, and that number has to equal 1. So let's actually calculate the equilibrium concentrations of A and B. So we know that A turns into B and it's reversible, and we know that the initial concentration of A is A0 and the initial concentration of B is nothing, and you're going to subtract minus x and plus x because there are coefficients of 1, and you get these two, and we know that KEQ is equal to the concentration of B over the concentration of A. So we can substitute those values and get 1 is equal to x, which we got for the equilibrium concentration of B, over the equilibrium concentration of A, or A0 minus x. Solving for this, we get that x, our change in concentration, is equal to the concentration of A initially over 2. So we know from this, by plugging x back in here and here, that the equilibrium concentrations of A and B are these two. So we are going to be dealing with a lot of variables, so watch out for that. Now, we have to know something else. So over here, we have the equilibrium concentrations, which is a great thing. Now, we know that A is first order, and since there's no indication that B has an order, we can assume that B is zero order, or in other words, the concentration of B is unrelated to its rate. So we can actually write the rate law for the forward reaction just like how we would do it normally. If they tell us that the order of A is 1, then we would write the rate of the forward reaction would be equal to K of the forward reaction, or you could just say K without the F, but I choose to do that to be more specific, and you multiply that by the concentration of A to the first power. Now the rate of the backward reaction will equal the K for the backward reaction times B to the 0, because we know that B is zero order, or we assumed that since there's no indication of it in the question, and we know that B to the 0 is 1, and we get that the rate of the backward reaction will equal a constant. So in other words, the backward reaction will stay constant because B does not have an order. So in a way, this is kind of like writing the rate laws for the elementary steps for an equilibrium reaction, but what's different is that this time you are not looking at the coefficients, because this A to B or B to A is a net reaction, so you cannot base it off of the coefficients. Instead, you are going to base your orders off of the information they give you. So they say A is first order, you're going to put that. If they say B is zero order, or they just don't talk about it at all, then you will say that B is zero order. And notice how the rate law for the forward reaction only involves the reactants, and the rate law for the backward reaction involves only the products. So keep a note of that, and remember don't base your orders off of coefficients, especially if they don't tell you that this is an elementary step, which they don't. So, we know that at equilibrium, the forward and backward reactions rates are equal, and we know the concentrations at equilibrium. So we could write a relationship saying that the rate of the forward reaction is equal to the rate of the backward reaction at equilibrium. So we can actually write a relationship here, and we can say that the rate of the forward reaction, which we know is here, and this is the rate law for the forward reaction, we can put it here, but instead of writing just the concentration of A, we could substitute it for the concentration that we know. And we know that at equilibrium, the concentration is 1/2 A0. So we could simply plug that in, and we get that the rate of the forward reaction is equal to the rate constant Kf times not just a random concentration A, but 1/2 of the initial concentration of A. So this is more specific, and this will help us solve the problem. Now we know that the rate law for the backward reaction is Kb, and thus, through this equality, we can say that the rate of the backward reaction can be written as Kf times 1/2 times the initial concentration of A. So I want to do this because I want to make it so that when I plug in everything will be in terms of A. So notice how I'm not dealing with Kb anymore. I'm being a little bit more specific, and I'm including A0 because, as you see in the problem, we have some A0s here, and I'm pretty sure we have to deal with that in the future. So better to be more specific than less specific. Now, before we continue, how do we use calculus language to describe the rate of the disappearance of A? Well, the disappearance of A will be negative since, it's disappearing, and thus the rate will be a negative number. So it's going to be the negative of the change in A over the change in time, or dA dt. Now we have to be a little bit insightful. We know that A is being consumed by the forward reaction, but it is being produced by the backward reaction at the same time. So the rate of the consumption of A, or rate A, is equal to the rate of the forward reaction, or the reaction that is consuming A, minus the rate of the backward reaction, since the backward reaction lowers the rate of consumption by producing A, so it's kind of counteracting what this is doing. So hence you are subtracting it, since if the positive value is consuming, then that means that production is going to be the opposite, or a negative value. So I hope you understood that explanation, but let's move forward. So we rewrote that here, and we now have to substitute it for things that we know. So rate of A is, again, negative dA dt, and the rate of the forward reaction turns out to be Kf times the concentration of A for any time. So we know that this is the rate law for the forward reaction. Now what about the backward reaction? Well, we said that the rate of the backward reaction will stay constant throughout the process since B is zero order. So the rate of the backward reaction, no matter what concentration things are, will always be a constant. And we expanded on this idea by making it so that the constant Kb is equal to Kf times 1/2 times the initial concentration of A. And this will allow us to write the rate of the backward reaction in terms of the initial concentration of A, which will help us solve this problem. And note that this is all a constant. So we substitute that here, and we get that Kf times 1/2 times the initial concentration of A will be the rate of the backward reaction. Now we just factored Kf out, and we're left with this, and now we actually have to do some calculus. So we are going to do the separation of variables. So let's see, negative 1 over A minus 1/2 times A0, and this is times dA, and this is equal to Kf times dt. So notice how I'm just moving things around here, and let me make the 0 a little bit nicer. And now we can take the integral of both sides. So the integral from time 0 to time t of Kf dt is equal to the negative, and our initial concentration is A0, and our final concentration is just any arbitrary concentration after time t, which can be written as AF or just simply A. And inside the integral, it will be 1 over A minus 1/2 A0 dA. Now we have to do some integration. So on the left-hand side, we can integrate it, and we get the negative of the natural log of A minus 1/2 A0. And this is all evaluated from, let's see, from A0 to A. And this is all equal to, well, we have to solve for that integral. And the integral of a constant is just the constant times a variable. So it would be kf times t, but the t is evaluated from 0 to t. And now we can do some simplification. And we get that, well, let me do a different color this time. The negative of, let's plug in a first. So the natural log of, well, let me put parentheses there, of a minus 1/2 of a sub 0. And we have to subtract, because that's how integrals work. We have to plug in a for A0 this time. So the natural log of A0 minus 1/2 of A0. And let's put that all in parentheses. And this is all equal to kf times, let's plug in t here and subtract it from 0. So t minus 0. And I'll just simplify that right away to t. Now we have this cool equation, and now we can do some algebra to fix it up. So we're going to distribute the negative. So the natural log of, let's simplify this, A0 minus 1/2 A0 is 1/2 A0. And we subtract that by the natural log of A minus 1/2 of A0. And we can do some algebra once again. And we could get that the negative of kft plus the natural log of 1/2 times the initial concentration of A is equal to the natural log of the concentration of A minus 1/2 times the initial concentration of A, A0. So notice how this is in the form of a line where this is y is equal to x plus b. So lo and behold, we just made a line, and we are comparing the y versus x. So the natural log of a minus 1/2 A0 versus t will give us a line. Which answer choice is that? Well, this seems like the answer choice, and B is our answer. Now, unfortunately, I didn't realize this earlier, but it's not negative dA dt, it's negative d concentration A dt, and I have to fix all of that, so let me fix that for you. And let's put brackets around that, brackets around that, and brackets around that, and brackets around that. So it seems like it's all fixed. So instead of writing dA, I write d times the concentration of A, because this is more specific and this is less specific. So that's all for this video. Have a nice day, everybody.